Hello, my name is Beatriz Garcia Ronzalez, and I am currently studying for a Master of Science in Chemical Engineering at the Technological Institute of Ciudad Madero. Today, I will present my work entitled Synthesis and Evaluation of a Zirconium-Modified SBA-15 Mesoporous Catalyst Impregnated with Phosphotungstic Acid for Triglyceride Conversion Processes. This research was carried out at the Petrochemical Research Center of the Technological Institute of Ciudad Madero with the valuable collaboration of my colleagues and advisors. Currently, the transition toward a more sustainable energy model requires the development of technologies capable of producing high-value fuels and compounds from renewable resources. Among the various avenues explored, heterogeneous catalysis has proven to be an efficient and versatile approach, especially when using modified mesoporous supports that offer high surface area, thermal stability, and the ability to incorporate specific active sites. SBA-15, an ordered mesoporous silica material, has emerged as an attractive support due to its highly organized structure and its ability to be functionalized with metals and solid acids. In this study, a zirconium-modified SBA-15 support, functionalized with phosphotungstic acid, was synthesized to catalyze the conversion of palm oil into energy compounds. Its structural and textural properties, acidity, and potential application in renewable fuel production processes were evaluated to optimize reaction efficiency and selectivity. Objective. The main objective of this work was to synthesize a mesoporous support of Zr-modified SBA for form and functionalize it with phosphotungstic acid, design an efficient heterogeneous catalyst, and characterize its structural and acidity properties to evaluate its performance in the catalytic conversion of palm oil into energetically relevant compounds. Methodology. First, pure SBA-15 was synthesized and subsequently modified by incorporating zirconium into its structure. The supports were then impregnated with different loadings of phosphotungstic acid. The resulting materials were characterized by nitrogen sorption for surface area and pore analysis, X-ray diffraction to confirm the ordered mesostructure, transmission electron microscopy and scanning electron microscopy to observe the morphology, temperature-programmed ammonia desorption to determine acidity. And, as we can see, Table 1 presents the nomenclature of the synthesized materials to facilitate their identification, along with their formula and a brief description of each. Table 2 summarizes the calculated number of acid sites according to the desorption temperature regions shown in Figure 3. Zr-1 exhibits mainly moderate, 57.43 millimole per gram, and strong acid sites, 61.7 millimole per gram, with low density, 196.94 mmol per square meter. 10% Zr-1 has fewer total sites, 71.61 millimole per gram, but a balanced distribution and higher density, 697.47 mmol per square meter. 20% Zr-1 shows the highest total acidity, 554.37 millimole per gram, dominated by strong sites, 347.38 millimole per gram, and extremely high density, 880.26 mmol per square meter, indicating a large number of accessible acid sites. Textural properties evaluated by nitrogen physosorption, Table 3, indicate high surface areas for SP and Zr-1, consistent with their preparation method. Impregnation with heteropolyacid reduces surface area, 104 and 33 meters square per gram for 10% Zr-1 and 20% Zr-1 respectively, and total pore volume, 0.1705 and 0.046 centimeters cubic per gram, but increases pore diameters, 66 and 57 angstroms, which may favor accessibility during catalytic reactions. Wide-angle XRD patterns, Figure 1, show that Zr-1 displays a broad peak around 25 degrees, characteristic of amorphous SBA-15, with good Zr dispersion and no crystalline zirconium oxide, favoring porosity. 10% Zr-1 shows additional sharp peaks, attributed to partial crystallization of phosphotungstic acid, enhancing acidic sites without compromising the SBA-15 mesostructure. 20% Zr-1 exhibits more intense and defined peaks, indicating higher crystallinity and greater active acid phase within SBA-15 while maintaining porosity and dispersion. SEM micrographs, Figure 2, reveal morphological differences. SP shows irregular, agglomerated particles typical of SBA-15. ZR-S1 displays fibrillar or rod-like structures. 10% ZR-S1 maintains dispersed fibrillar particles, whereas 20% ZR-S1 shows larger, more agglomerated particles, reflecting phosphotungstic acid accumulation. The desorption thermograms, Figure 3, reveal that ZR-S1 has a strong peak at 300 to 500 degrees Celsius. Moderate sites. 20% ZR-S1 presents peaks at 500 to 600 degrees Celsius and 750-850 degrees Celsius, strong sites of different energies, and 10% ZR-S1 shows weaker signals with peaks at 100 to 250 degrees Celsius, weak sites, and around 700 to 800 degrees Celsius. SP exhibits minimal acidity, as indicated by an almost flat profile. Figure 4 shows the transmission electron microscopy (TEM) analysis of the ZR-S1 sample at 50 nanometers reveals a highly ordered structure characteristic of zirconium-modified SBA-15. A uniform arrangement of parallel channels is observed, typical of the hexagonal pore structure of SBA-15. The incorporation of zirconium does not significantly alter the Mesoporous organization, as the regular channel arrangement is preserved. No segregated zirconium oxide particles are detected, indicating homogeneous dispersion of zirconium within the silica matrix. This behavior is favorable for catalytic applications, ensuring efficient access to active sites without blockage of the mesoporous channels. Discussion results indicate that the mesoporous structure of SBA-15 was preserved after zirconium incorporation and phosphotungstic acid impregnation, as shown by XRD and SEM. Although surface area decreased, pore diameters remained in the mesoporous range, allowing proper molecular diffusion. This reduction is due to partial pore blockage by impregnated species. However, the ordered structure remains stable, which is essential for heterogeneous catalysis. TPD of ammonia profiles showed increased total acidity with higher heteropolyacid loading, suggesting improved catalytic potential for acid-driven reactions such as triglyceride conversion. Maintaining an ordered mesostructure while significantly increasing acidity is challenging in heterogeneous catalysis. These results indicate that our catalyst is both structurally stable and chemically optimized for industrially relevant processes, such as biodiesel or green diesel production from palm oil. Conclusions. The incorporation of ZR into the SBA-15 framework followed by impregnation with heteropolyacid resulted in well-defined mesoporous materials, with no evidence of crystalline zirconia phase formation. Although the specific surface area decreased due to modification, the ordered mesostructure was preserved. The increase in total acidity, particularly in samples with higher phosphotungstic acid loadings, highlights the catalytic potential of these materials for triglyceride conversion processes, such as those involving palm oil, offering an efficient and sustainable route for the production of clean fuels from this oil. Overall, this material represents a promising platform for the development of efficient, durable, and environmentally responsible catalysts for sustainable fuel production. The retention of mesoporosity ensures that bulky molecules, such as triglycerides, can effectively access active sites, avoiding diffusional limitations that often reduce efficiency in biomass conversion processes. The presence of both Bronsted and Lewis acid sites, particularly in the medium to strong range, allows the effective promotion of complex reactions such as esterification, trans-esterification, and cracking of oxygenated compounds, extending the catalyst's applicability to various renewable feedstocks, including waste cooking oils and algal lipids. I would like to thank the National Institute of Technology of Mexico, Ciudad Madero campus, and other technological institutes and research centers for their support in the realization of the analyses. I also extend my gratitude to the National Council of Sciences, Humanities, and Technologies for the financial support provided for this project, and to my advisors and colleagues for their collaboration. If you have any questions or need more information, please do not hesitate to contact us at the following email addresses. Thank you for your attention.